Section 10.4 is solving radical equations. I can solve equations containing radicals, and I can identify extraneous solutions. Those are our learning targets and what we're shooting for here in this section. Big ideas. Some radical equations can be solved by squaring both sides and testing the solutions. When extraneous solutions are tested, they do not solve the original equation. A radical equation is an equation that has a variable in the radicand. To solve a radical equation, get the radical by itself on one side of the equation. In example 1 here, we're going to be solving by isolating the radical. So to find our solution here, I'm going to try and get my radical alone. And we do it this very similarly to how we got our variable alone before. So right now it's being added by 7, so we're going to subtract 7 to get that to be 0. Again, the only thing I want on the left side is that radical. So plus 7 minus 7 gets me to 0. And all I have left is square root of x equals 9. Now, to get rid of something square root, we're going to square both sides. We're going to undo that operation. So square rooting and square are inverse operations here. 9 squared is 81. So this is probably our answer, but we should plug it in to double check. Square root, instead of having an x, I'm going to put in an 81. And check the rest of my equation. Square root of 81 is 9. And 9 plus 7 equals 16. So 16 does equal 16, which means our solution is right. When we have radical equations, we really want to plug in our variables, not only to make sure that our number's right, but to make sure that our answer still works. And we'll talk about that a little bit more in this section. Now, feel free to pause here and give this a try if you'd like. Again, we're going to try and get our square root by itself. One thing to consider, guys, and we've talked about this before, but right here is where that bar ends in our square root. That means that that's the only things in our square roots are the things that are underneath that square root bar. So just the x here. That minus 5 is its own individual term. So to get rid of a minus 5, we're going to add 5. Square root of x equals 3. Now again, to get rid of my square root, we're going to square both sides completely. So we're going to completely square the left side and get just our radicand, whatever's inside our square root is all we have left. And on our right side, we square the entire thing. 3 squared gives me 9. That's our solution. Let's double check it here. Square root of 9 minus 5 equals negative 2. Let's check. Square root of 9 is 3. 3 minus 5 is negative 2. And negative 2 does equal negative 2, so it checks, and we are correct. In example 2 here, we're going to be using a radical equation. The time t in seconds it takes for a pendulum of a clock to complete a full swing is approximated by the equation t equals 2 times the square root of L divided by 3.3, where L is the length of the pendulum in feet. If the pendulum of a clock completes a full swing in 3 seconds, what is the length? Here we're going to round to the nearest tenth of a foot. So it tells us here our equation. It also tells us what we're looking for as far as time. So we're going to plug that in for t. And we're trying to find the length to the nearest tenth of a foot. So I take my equation and I substitute in what I know t to be. And since we're talking seconds here, I know that's my t value. So 3 equals 2 times the square root of L divided by 3.3. And again, we're looking for length, so I only have one variable left, it's L. That's good. Now, my first step is to get my radical by itself. And in order to do that, I get rid of my multiplication by dividing. We're going to try and get rid of our square root, and in order to do that, we square both sides completely. 1.5 squared is 2.25. And when I square a square root, I just get my radicand. I just get whatever's inside. Now, to get rid of my division, I'm going to go ahead and multiply. And when I do that, on both sides, I get 7.425 equals L. We're rounding to the nearest tenth of a foot, and L is length in feet. So the 10th spot, 2 decimal places after is where I look. So I look at the 2 rounds down, so 7.4 feet is my length. Again, our final answer is only going to have 1 decimal place, so we look 2 spots behind it, 2 rounds down to just 7.4. Now feel free to pause here and give this a try. How long is it if each swing takes 1 second? So our formula here, t equals 2 times the square root of L divided by 3.3. My time is 1 second. So I take that value and substitute it in for t. And we're looking for how long, so we're talking about a length because it's of the pendulum, not time. First step is to get our radical by itself, and I do that by getting rid of my 2. I'm going to divide. Now, to get rid of my square root, since that's the only thing I have left on that side of my equation, I square. And I square both sides completely. Sorry, there's a 0.5. 0.5 squared gives me 0.25. And when I square a square root, all I get is my radicand exactly as it's written. So L divided by 3.3. To get my L by itself, I get rid of my division by multiplying. And here, I'm going to get 0.825 feet. And it doesn't specifically tell me to round to the nearest tenth here, but since it did on the last one, I'm going to go ahead and do that. 0.8 feet. So I would have taken either one of those answers there. In example 3 here, we're going to try and get our radical by itself. But if we look, we have 2 separate radicals. And the left side and the right side are both as simple as we can get them without getting rid of that square root. So we can go ahead and square both sides right away. And when I do that, I just get my radicands, what's inside my square root, exactly as it's written. 5t minus 11 equals t plus 5. I'm going to get my variables together on one side. Because I have a linear expression here, I just have t to the first power, first degree t's, so I can get all of those together in one spot. And now I get it by itself. Once I have them combined, I get it alone. I'm going to add 11 first. And then to get rid of multiplication, I'm going to go ahead and divide. And we should double check this. 5 times 4 minus 11 is the square root of 9, which is 3. And 4 plus 5 is 9. Square root of 9 is also 3. So that checks, and our answer is correct. Feel free to pause here and give this a try. So to get rid of my square roots on both sides, I'm going to go ahead and square my left side completely and my right side completely. And when I do that, what I get is what's inside my radical. Same thing on my right side, I get what's inside my radical, my radicand. Now, I try and get all my variables together on one side. And here, since they're both linear, I just have 2x minus 4 equals 10. And now from here we evaluate, now that all of our variables are together on one side, what do we do next? Well, here I just have x in one spot. It's linear. So I'm going to go ahead and get that x by itself. To get rid of a minus 4, I add 4. Then divide by 2 to get rid of my multiplication. And I get x to be 7. Let's plug it in and check. 7 times 7, 49. Minus 4, square root of 45. 5 times 7 plus 10 inside my square root. 35 plus 10, square root of 45. So that checks, and it doesn't matter here, guys, that my radicals don't simplify to whole numbers, they just have to both be the same. When we solve an equation by squaring each side, sometimes the new equation we created has solutions that don't work in the original equation. When this happens, those solutions are called extraneous solutions, and those are solutions that do not satisfy the original equation. So we always need to substitute our values back into our original equation, that's important, to make sure they work, especially anytime we do things like square roots or squaring or any kind of changing things like that. So in example 4 here, there's nothing I can do to get my radical more alone. If I look, that bar is over my n plus 12, so this entire thing here is my radical. So to get rid of it, I square each side in its entirety. So n squared equals, when I square a square root, I just get my radicand, or what's inside. Now I want to get all my variables together on one side, but I cannot combine those. Those are not like terms. So here I have a quadratic because it's n squared, and I can't combine them, so I'm going to get it set equal to 0 because I have that quadratic and linear terms, second degree, first degree, and now I'm going to try and solve from here. So I'm going to try and factor first, multiply to 12, subtract 2, 1, 4 and 3. So to multiply to n squared is n and n. Since I subtracted, I'm going to find use different signs. 4 is bigger, so it gets a sign in the middle. From here, I can use my zero product property, which says that n minus 4 equals 0, or n plus 3 equals 0. That's the only way we can multiply to 0, is if one of our factors or the other or both happen to be 0. To get n by itself, now I can add 4 and subtract 3. Now, we need to double check here and make sure both these answers work. So I plug them into my original equation. And when I do that, guys, what I mean is the equation that I had to start off with. So before I squared it, before I changed anything at all. So here that's going to be the n equals square root of n plus 12. So I'm going to try 4 first. 4 equals the square root of 4 plus 12. 4 plus 12 is 16. Square root of 16 equals 4. So 4 equals 4, checks, and that works. Second one is negative 3, so I plug that in for n. Negative 3 plus 12, 9. Square root of 9 is 3. Negative 3 does not equal 3, so that's an extraneous solution. Okay, it looks like it would work, and for this equation here it would, but that's not our original equation. Our original problem is here, and the negative 3 doesn't work, just the 4. So my only solution there is n equals 4. Feel free to pause here and give this a try. Because my square root is all the way by itself, I'm going to square both sides. And when we do that, we square both sides in their entirety. So here, when I square a square root, I just get my radicand. But on the left side, when I square here, keep in mind I'm squaring both pieces. So the negative 1 gets squared to a positive 1, and the y squared gets squared to a positive y squared. When we square a number, it's always going to be positive. We'll get our variables together, and since it's quadratic, I'm going to move and get it set equal to 0 right away. Y squared minus y minus 6 equals 0. It's usually helpful if our y squared is positive, because from there we can try and factor. Multiply to 6, subtract to 1, 3, and 2. 3 is bigger, so it gets a sign in the middle. Zero product property says we set them both equal to 0. Either add or subtract. Y equals 3, y equals negative 2. Now, when we plug them back into check, we plug them into the original equation. So minus, and then my value for y is 3. And I get negative 3 equals 3, which is not true. I try 2 minus negative 2. And I get 2 equals 2. That one works.